Now, we should look forward to understanding the more about the ice sections. So, ice sections shall be considered within the alpine regions, and ice sections may need to be considered in areas where there are local records or experience indicating that ice accumulation may occur. Now, what are the the structures which are most prone, or we can say sensitive to the ice sections? There are these masts, there are these telecommunication towers, antennas or antenna structures, cables, or we can say ropeways, structures for ski lifts, or we can say exposed buildings are part of them, or towers for special type of construction such as transmission line, wind turbines, or similar kind of structures. I just want to show you one photo. That is a classic example of the ice action. So in here we can see that basically this is the telecommunication tower we can see here, and you can see that how the ice action can is visible. Like you can see that how the ice is formed on the different structural elements. There on the top you can see the ice also, and here also on the platform you can see the ice. And as per the course, it is not that we can unlike in wind and earthquake, we do not take these actions together. But if we're talking about the snow, we do consider, and if we're talking about the wind actions, we do need to consider the some percentage of snow at a time of the wind and some percentage of snow at a time of the earthquake also. So snow load is not that load which is like once in a while. That load is like is there for, let us say, in this area for the snow month, that is for, let us say, for 2 to 3 months, this snow may be formed on this particular structure. So on the basis of that, we do consider the appropriate action of snow in combination with the wind and in combination with the earthquake. So the second question comes that how we can consider the thickness, or how we can consider the action of the wind with the snow. So that we shall discuss shortly. But if we're talking about the ice thickness, so in the absence of site specific data, the ice coating thickness for ultimate limit state for all function categories shall be for mh equal to 1, it shall be 30 mm on all faces, and for mh greater than 1, it shall be 100 mm on the windward face and 30 mm on the rest of the faces, that is at the leeward face. What exactly is mh? mh that we already discussed when we were discussing about the wind loads, that is it is the hill shape multiplier obtained from AS NZS 1170.2. But at the same time, if we're talking about the serviceability limit state, we do need to consider only 10 mm on all the faces, unlike 100 mm when we are talking about the ms greater than 1, and if we are talking about the this limit state design or ultimate limit state design. So that is the basic criteria. Density of the ice that can be taken as 915 kg per meter cube. So after that, if you're talking about the static ice loads, so static ice loads are what we mean is that different types of structures are more or less sensitive to various aspects of the ice sections. So the structures are maybe stretched out steel ropes, cables, mast guys, slender lattice structures, antennas and antenna structures, or we can say covering materials such as cladding. So most vulnerable type of structures are cables, ropes, and light lattice structures, that is guide mast. And dynamic effect need to be considered for these kind of structures. Why? Because these angles are, or we can say these structures are not made with very heavy sections. They are either made with the L angles or C channels, and they are like we can say very much sensitive to wind action also, earthquake action also, and in combination with the ice action also. So we do need to think carefully when we are designing these kind of structures in alpine or subalpine regions. Now, the second thing is that how we can assume that the wind shall be, or sorry, the ice shall be accumulated, or we can say how we can say that the area for the effective area for the wind shall be increased. So in here you can see that if this is an I section, So if this is an ice section, we do need to understand here that when we're talking about the accumulation of the ice, so the ice shall be accumulated on all these faces, something like this. And this is the thickness T that we have already discussed a few minutes back. That for mh less than 1, the thickness needs to be approximately 30 mm, and that needs to be 10 mm when we're talking about the serviceability limit state. Similarly for C channels also, the ice shall be accumulated something like this for L angle also, and for circular hollow sections also, or wires also. So it is not that we're talking about the hollow sections only, we're talking about the solid sections also. So let us say we are designing a transmission tower from one point to another, and this is the wire. So on this wire itself, we do need to consider this thickness T, and whatever is the load that is coming here at the supporting point, that load has to be self weight of the wire plus weight of the ice that is accumulated on all the periphery. So both the dimensions of the structural members are subjected to changes, and the reasons are likely amount of accumulation, shape of accreted ice, and drag coefficient. Now, drag coefficient is the concept that we have already discussed when we're talking about the wind dynamics, that the wind flows, and on this particular area or on the edges, the main action of the wind happens, and we do have to consider the drag coefficient appropriately as per the shape. So drag coefficient shall be different for I section, it shall be different for circular, it shall be different for square and rectangular also. So this is also one of the example where we can see that how the roof or we can say the roof is sensitive to the accumulation of the snow. So this additional load that has to be resisted by this particular roofing arrangement. Similarly on the left also you can see various pictures and how the snow action can be harmful for the roof if it is not properly designed. So after that, if we're talking about the snow action, so procedure for use in determining the values of the snow action shall be as per AS NZS 1070.0. That is a general statement. After that, if you're talking about the roof snow load on a sloping surface, so this is basically the sloping surface, and this the load that we can assume it as, let us say the ice is accumulating something like this. So we can make it as an equivalent, we can say uniformly distributed load on both the sides. So load shall be assumed to act vertically. Unlike wind, in wind action what happens that we do consider the local axis, but at the time of the, we can say, snow, we do not consider the, we can say, local axis, we do consider the global axis. So unlike wind, it acts something like this, but at the time of the snow action, the load is something like this. So after that, snow will be usually present of roof of structure for approximately 3 months of the year when we're talking about the alpine region. That is not valid for the subalpine regions. And balconies are also most susceptible to damage of the snow actions, because many times we have seen that balcony is usually open. So let us say this is the building and this is the balcony. So at the time of the, we can say, snowfall, the snow may accumulate here also. So we do need to ensure that whatever bending moment we are considering at this particular point, we do have to take the weight of the snow also. And what shall be the weight of the snow, that we shall discuss shortly. The code is helping us to calculate the snow load. So this is the typical example of calculating the snow load on the roof. Now in here we do have 3 different terms, SG, CE and mu I. So snow load on the roof, that is named as S. After that, that is equal to SG. What exactly is meant by the SG? SG is the characteristic value of the snow load on the ground. Now what exactly is the characteristic value? Characteristic value is the value that still has a probability of exceedance by 5%. That is 95% of the times we can say the value shall be lesser or equal to that, but there is a 5% probability of exceedance of this particular loading value, and this value is given in kN per square meter. So let us say if you're talking about the New South Wales, and if you're talking about the, we can say, Mount Blue Cow. So height above the elevation, above Australian datum height, that is basically 1900 meters. Terrain classification is in between 1.1 to 3. So for ground snow load SG, for we can say probability of exceedance. Now in majority of the cases, this is the probability of exceedance for the strength limit state, and this is the probability of exceedance if you're talking about the serviceability limit state, or if you're talking about the structures which are, we can say, having very lesser importance. So in here we can see that in majority of the cases it is 1 by 150. And if you're talking about the Mount Blue Cow, the value of SG, that is between 17.7 to 32.9 kilonewton per meter square, or kPa. Now I must say that this value is high. This value is not less, because if you're talking about the putting the value of 17.7 kN per meter square, value of the SG, that is very high. So we do have still higher values. Let us say if you're talking about this particular zone, which is having height of 2.228 meters. Here the value is as high as 66.2 kPa. So if we are having a structure near to this particular the level, we do need to take the appropriate value of the snow actions. So after that, that we have understood that SG is the value that is as per the location. After that, CE value. CE is the exposure reduction coefficient. So for subalpine region it is 1. For sheltered roof it is 1. For semi-sheltered roof it is 0.75, and for 0.6 that is for the wind swept roof. So if you're talking about the sheltered site where roof is protected from the wind by obstructions such as other structures, terrain features, or number of closely spaced trees higher than the roof. Semi-sheltered means that a site where the roof is only partially protected by numbers of scattered obstruction higher than the roof, that is scattered trees. Wind swept is the areas where we have considered that site where the roof is exposed on all the sides with no protection provided by obstruction, trees, or terrain features higher than the roof. So in that particular case, exposure reduction coefficient CE shall be considered as 0.6. So after that, the third is the shape coefficient mu I. So mu I is basically as per the shape of the, we can say, roof itself. So if we are having this particular monopitch roof, so in this particular case, the value of the mu I is basically 0.7, 60 minus alpha. Alpha is basically the angle here. So let us say this angle is 10 degree. So 60 minus 10, and that needs to be divided by 50. So whatever is the value that we are getting here, that has to be between 0.7 and 0. So that is like the basic, the first load case, whatever value that we are getting. Second load case shall be that only the half of the roof is loaded, other half is unloaded, and that do usually happens because of the shape of the roofing. Sometimes it do happens that the snow gets heavily loaded here and very lightly loaded here. So the snow forms a pattern of something like this. So that is why it is taken as 0.5 mu I, but it is considered only on the half the height of the roofing arrangement. So that is how we can calculate the value of the, we can say, SG, CE, and mu I, and according to that we can calculate the value of the S, that is the snow action. After that, the in majority of the cases there is this snow overhanging from the edge of the roof also, and that is, I must say, it is a very risky, because it can be it can fall on our head also, and it can lead to accident also if this particular this snow falls. So that is why in majority of the areas there are these ice breakers that are installed, so that these kind of formation does not happen. But if we do not have any other option except to consider this kind of action, the code do help us in calculating the snow overhanging the edge of the roof. So design of those part of a roof cantilevered beyond the edge of the wall shall take into account the snow overhanging the edge of the roof. So that formula is basically K multiplied with SG, CE, mu I, that we have already understood, to the power 2, divided by the gamma. Gamma is the average weight density of the snow in Kn per meter square. and K is the coefficient to account of the irregular shape, that is usually taken as 0.5. SGCE mu that we have already discussed, and SE is basically the snow load per meter of the roof due to overhanging. So this is basically the value of the SE that we do need to calculate. So these are the various values that or concept that you do need to understand. Now let me just revise all the concepts that we have understood. The important concept that we have understood is that the snow load can be calculated as SGCE mu I. SG is the characteristic value that can be taken from table 5.2. CE is the exposure reduction coefficient that is different for different conditions, and mu I is the shape coefficient that is dependent on the shape of the roofing arrangement. Before that, we have understood that what exactly is the snow action. The snow action shall always be taken in the direction of the gravity itself, unlike wind, which is usually taken on the local axis. Before that, we have understood about the effect of the ice on the structures. We do need to consider the thickness of the ice in calculating the total effective area and the self-weight of the structure also. The most susceptible are the wires and ropes. So if we are designing the transmission towers, we do need to consider the accumulation of the snow, and according to that we do need to calculate the dead load or self-weight of the structures. Ice thickness is taken as 30 mm for mh equal to 1. For ms greater than 1, it is 100 mm on the windward phase, 30 mm on the leeward phase. And for the serviceability limit state, irrespective of the value of the ms, 10 mm needs to be considered.